want to keep in mind that this is bent, so it's polar. Water's a liquid. So at first, if I wanted to think of how water acts, I would think that there is some bond, some hydrogen bond, going back and forth between the oxygens and the hydrogens. But if I draw it like this, now I think that for a liquid, the bond always stays in the same place. But liquid, we know that liquid molecules move around. So that can't be true. Get rid of that. So then the way I want to think of these is it's as if there was an area around this water molecule. Where it is going to be having these intermolecular forces with other water molecules. Okay, so now if I'm picturing water, I want to picture a bunch of these areas. So let me make this a little smaller. Yeah. Go, get rid of this guy, and just make a bunch of these. Okay, so these water molecules are moving all around, but their intermolecular forces are still working in between each other. So the green is this area of intermolecular force. I'm not drawing it straight because I'm talking right now about a liquid. Now, into this liquid, let's say I wanted to add silicon disulfide. That is linear. It's just like carbon dioxide. Since it's linear, it is not polar. Now, hydrogen bonds are dipoles. So what this wants to do, if I put this into the solution, take this out. If I stick that into the solution, the problem is, smaller, it is not able to make a dipole bond. So it is not able to bond with the water. So it is not like this is a part of the solution, but it is going to be in the solution, kind of surrounded by the other water molecules. It's not really dissolving. In fact, I would be able to see it because it's not dissolved. Okay, and that's based on its shape. What if I had something like, let's take pH 3. That is polar. It's pyramidal. And so it is able to make dipole bonds. Oh, those things didn't come with it. There we go. Since it's able to make dipole bonds, what I can do then is I can take a water out, and I can put this guy right in there, and it's able to make dipole bonds with the other water molecules. Now, the other water molecules don't necessarily notice so much that there's a new molecule in here. They're still able to make dipole bonds with it. They're still able to be attracted to it. So they surround it, and if you look, it still has kind of the same makeup as it did before. Since this is dissolving, now this has colligative properties. What happens if I add a salt? If I add NaCl, now it doesn't just dissolve, but when NaCl goes into the solution, there's so much attraction to both of these that NaCl is going to dissociate. Right. So I've got ions that I'm putting into the solution. I probably shouldn't have done that, should I? Okay. Sorry. So chlorine will go in. Sodium will go in. And now I've got bonds that are dipole bonds between ions. So we'll call this like an ion dipole bond. However, the waters are still attracted to these things and they're dissolved into the solution. NaCl, when it goes in, comes apart into sodium and the chloride. So that's got a Van 't Hoff factor of 2. What if it wasn't sodium chloride? What if it was sodium sulfate? Now I throw this into the solution. It's ionic, so it separates, it dissociates. The sulfates, since those are polyatomic, they stay together. The sodiums do not. The sodiums will separate, and so I'll have 2 sodiums, and I'll have the sulfate. Oh, sorry. So now when I throw this into solution, I've got a spot for the sulfate, I've got a spot for the sodium, I've got to kick out another water molecule and get the other sodium in there. This time I've got 3 going into the solution, so that factor, that N factor, is 3. Now, if I start heating this up, what's going to happen is that these intermolecular forces, if this is the surface, these intermolecular forces can get broken. As I start heating it up, they move fast enough to break free from these intermolecular forces, so take that away. And now this water molecule is liberated. It's become a gas. It's going to be moving around. It's going to be colliding with things. When it collides with the surface here, that's called our vapor pressure. So as soon as we start to get things breaking their intermolecular forces and freeing themselves, you're going to get a vapor pressure. Now that'll happen for all liquids as soon as you go above their freezing point. And as you give them more energy, as you raise their temperature, you're going to break more of these bonds. Let's throw them in this little trash. And you're going to get a lot of these things moving around. You are going to be increasing the vapor pressure. In fact, you will increase the vapor pressure with temperature all the way up to the boiling point. At the boiling point, the pressure outside, so the pressure in the air, would equal the vapor pressure. There would be so much gas there becoming liberated, so much water molecules freeing themselves, that that pressure would equal the pressure in the room. And at that point, now all of a sudden, we're getting all of these to break. And so the water molecules, they're above their boiling point, they free themselves. But sulfate and sodium are not above their boiling point, which means that they need to come back together and form salts at the bottom. That's going to take more energy. It's going to take more energy for that salt now to reform, and it's going to take more energy for the water molecules to get out of the way of all those other ones and become a gas. That's why the boiling point increases. Get the last ones out of the way. Okay. Now, the opposite is true as water is going to freeze. So let's say we would take this gas and I'm going to freeze it right away. Okay, so I like throw it up into freezing cold air and the gas freezes, turns into snow. What happens now is now I get to draw these intermolecular forces as if they were a solid, because they are a solid. Okay, do I want one more? Sure, there we go. The problem here is now if I want to put pH 3 into the solid, into the ice, pH 3 is not able to make these intermolecular forces, not able to make these bonds with other water molecules as it is a solid. In fact, all solids, as they freeze, stay as pure chemicals. You cannot get chemicals to form mixtures as they freeze. I think the one exception is metals. Even if you go out and you look at rocks, as rocks cool, as liquid magma cools, those chemicals inside of liquid magma, they do not combine. They separate out, and you can actually look on granite and see the chunks of each different chemical that as it cooled was pushed away from each other. So as these things become solid, they are not able to form bonds with other chemicals. They have to form their intermolecular forces with themselves. which is why as ice freezes, it's going to kick out all the salts and put them on the bottom, because the salts are not able to get into those intermolecular forces. That's why it takes a lower temperature to freeze salt, because now it has to to freeze water with salt dissolved in it, because now it has to kick all that salt out. Water, on the other hand, is bent and it's polar, which means that water does not dissolve in air, or it doesn't dissolve very much in air. So, if you're driving around and you notice at night that you see fog, you fly through a cloud in a plane, what you're seeing is the actual water there that's not dissolved in the air, but that is suspended in that solution. And now what happens is that if light is coming through, if it's coming through a place where nothing's dissolved, it's going to keep going through straight. But if it's coming through a place where there are particles and those particles aren't dissolved, what happens now is the light is going to interact with that water. And instead of going straight, what happens is that the light gets bent. And as it does, the red colors will get bent the most, the blue colors will get bent the least, and the green is in the middle. Look at that, I've got green. And this is called the Tyndall effect. Anytime you have particles that do not dissolve and are suspended in the solution, you will get the Tyndall effect. Now, if it dissolves, you get colligative properties. If it doesn't dissolve, you get the Tyndall effect.